welcome to another episode of Planet Hunters Coffee Chat. In lieu of Cassie not being here, as you might have noticed, I am Cole Johnston, and we are here with the lovely Nora Eisner.
Hi Cole, how are you doing?
Doing pretty good in yourself?
Yeah, I'm not too bad. I'm enjoying not having my thesis to write anymore.
I know, it's a great feeling, isn't it?
It is, absolutely.
Now just the regular stress can come flooding back in. It's awesome.
Exactly, yeah. You have to trade off, different sources of the stress. Why not?
Right. So today, I think we're going to be talking about something that I really, really like, and I've been alluding to throughout some of the videos that I've been fortunate enough to sneak my way into, and that's something called asteroseismology.
Yes, I'm actually really excited to do this video, and I feel like I mentioned my excitement for this quite a while ago already. And yeah, I think you also mentioned it a couple of times. I should say, you are the expert in asteroseismology, not me. Yep, you. That. And I think you should be the one to explain this. So I think we always have this debate. I'm the star person. No, cut that. I'm the planet person.
Stars for the win.
I'm the planet person and you're the star person. So we're talking about this today. It is related, or can be related, to the study of planets. Understanding your star helps you understand your planets. Those two are very, very linked together, intrinsically linked together. So why don't you start off by telling everyone what asteroseismology is and how it works?
Okay, I can do that. So asteroseismology is a really fun topic and a really odd word. So it's not just asteroseismology, it's asteroseismology. And somebody once explained to me that it's asteroseismology because you have to make the Latin and Greek roots of the words match. But the logic behind that is lost on me, and that's why I do science. So asteroseismology refers to the study of stellar interiors through the analysis, the observation of stellar pulsations. And stellar pulsations are something that we've talked about a couple of times in various episodes, where we're looking at the light curve of a star, and you just happen to see these wiggles that come up and down, and you might go, what the heck's going on here? Well, that's because the changes in brightness are caused by the star changing temperature and the size on its surface ever so slightly, and that gives rise to brightness variations that we can see with a telescope. Now, how does this help us with anything, you might ask? And I think in a previous episode, I had explained that pulsations are kind of like starquakes, right? So in the way that the Earth has earthquakes, and seismologists here on Earth use earthquakes to study the Earth's interior, stars are starquakes, and I use these starquakes to study the interiors of stars.
That's cool. So one analogy would be, so you can use these quakes to study, I don't know how I do this, these quakes to study kind of what the star is made of. So an example, apart from the Earth, which is already a good example, would be if you have different sized bells. If they're made of different materials or if they have different sizes, they ring differently.
Yes. Now, I know you're only doing this because you have props and you want to use them.
I really want to use them.
So, yes, just briefly to help lead into your use of props. The size, just in the way that the size, shape, and composition of a bell determines the frequency or the pitch with which a bell rings, the size, shape, and composition of a star determines the frequencies, or the pitches with that a star rings at. And then you have your little demonstration. So let's have at it.
I'm so happy that this came up so naturally, this demonstration. So I have, because this is coffee chat, because I don't have any bells, we have 2 coffee mugs of different sizes. They are made of the same material, but they do have different shapes. So we will ring both of them.
You heard that pitch? This one has a different pitch. And yeah, this is related to just the difference in the size and the shape of those 2 cups. So if you were to be in a dark room, not be able to see anything, but you were to hear these 2 pitches, these 2 clinks, you'd be able to tell that you're listening to somebody sitting there banging 2 different coffee mugs. And that's what I do with stars. in a slightly more sophisticated manner, I hope.
So what is the main property that you hope to find out from doing this analysis of these pulsations?
Well, so there's actually quite a lot that you can tell from about a star from its pulsations, right? So I think we've also talked about this a little bit. All different kinds of stars pulsate, and they all have their own class of star. Each type of star has its own subclass, its categorization based on how it pulsates. We'll get back to that in a second, I think. But the things that you can determine from this are how quickly the star is rotating, which is otherwise very difficult to do unless you have spots on the surface. You can tell how spherical the star is. Actually, there was a really fun study in 2014, I think, that found the most spherical object in the universe through using asteroseismology.
How do you find out how spherical it is from the pulsations?
Well, basically, you have to assume that a star is a perfect sphere, and you can measure the deviations from this perfect sphericity based on how different the observed frequencies are from the theoretically predicted frequencies for a perfect sphere.
Oh, cool.
So those are some things. You can also determine just generally the size. So how large the radius of the star is, the mass of the star. If you're lucky, you can determine the sound speed inside of the star. So just, if you go into if you have two different rooms that are different temperatures, but everything else is the same, the speed of sound in those rooms will be different, or even more, maybe a little bit more helpful. If you've ever been underwater in a pool and somebody clacks two stones together, you can see the stones clacking before you hear it, and that's because there's a sound speed difference.
Oh, I've never done that experiment. Really cool.
So if you're fortunate enough to have a pool, you can go and try it. Or if you want to go to your public pool and be a nuisance, you can try it there as well.
Always great advice. So from those properties that you mentioned, the ones that are probably most relevant to exoplanetary science are the mass of the star and the radius of the star.
Yes.
So what asteroseismology gives us is these properties to a precision, so much better accuracy, precision than other methods. And that's really, really good because those two parameters, so both the radius and the mass, are absolutely crucial if we want to determine the mass or the radius of our planet.
Certainly.
So that's why asteroseismology, well, that's why I think asteroseismology is so cool, but it obviously has other uses too.
Yes. I try to use it to determine the what's happening at the core of a star itself. But I can understand that some planet people want to use it to find out the mass of their planet. I get that.
It's all about the planet. Cool. So I have another question. So when I did my illustration with the cup, I had to hit it in order to hear that sound. So what drives these pulsations? And also, I guess closely related to this, we've seen lots of different light curves on these coffee chats so far, and we saw pulsations on a completely wide range of different scales. So what kind of scales are we talking about? Are these kind of the slow pulsations, or are they the very quick, rapid oscillations?
So all these different kinds of stars have different types of pulsations, right? The bigger stars typically have longer period pulsations just because they're larger, right? So one of the very easy things you can do is if you know in what range the pulsations occur, you can make a relative guess as to this one being, larger and cooler or younger and hotter, something like that. But in general, stars they produce enough energy inside themselves to just shake the star enough that it pulsates. So as I said, there's tons of these different classes, and maybe we can even have a couple of episodes on those in the future if that's something that people would like, and you can mention that in the comments. And I've always wanted to do this, comments below. But in this case, we're going to be talking about things that oscillate like our sun. They pulsate like our sun. And because astronomers are really good at coming up with original names, we call these stars solar-like oscillators. Right?
We're very inventive, what can we say?
Super inventive. Very descriptive, maybe not so original.
So I think we'll look at an example of a solar-like oscillator today with some code, and and see what that can tell us.
Yeah, I mean, but so just before we get to that, I think it's important to know that it's very hard. So in some of the other cases, like the Gamma Doradus type pulsator that we saw in one of our light curve of the week challenges, those are very clear. You see these large scale variations on the course of hours. Solar-like oscillations occur somewhere on the order of 5 minutes, somewhere in that range. Let's say 3 to 10 minutes. Typically. And so it's very hard to see those as individual points in a light curve. It just looks like scatter, right? So in order to really tell if if a star has solar-like oscillations, we can't look at the light curve. We actually have to look at the periodogram, which is something that you guys have taken a look at 2 episodes ago.
And yeah, so that's a good point. So also, if we think that TESS has a cadence, it takes an image or a data point every 2 minutes. If that pulsation is on a time scale of 3 minutes, that's very difficult. Gets very difficult to see.
It's hard to see. Yeah.
It's difficult to see the trend, but also difficult to pick it up. But hopefully, with the periodograms, and do rewatch that episode or watch it for the first time if you don't know what we're talking about. But yeah, let's have a look at some of those periodograms for a solar-like oscillator. So I will share my screen. Okay, cool. So today we're going to use a notebook that I didn't write. Cole didn't write it either. It is a notebook that's provided by the Light Curve package. So we've been using Light Curve throughout all of our videos. That included coding. So this is, we'll put the link as part of the video description, but this is on the Light Curve website. And they have written this fantastic module that lets you analyze these, as Cole mentioned, these solar-like oscillators, so these stars that oscillate like our sun, to determine properties of these types of stars. So we'll go through the notebook or through the code. You can download this code right from the website. So we're at the top here. I'm going to make this a bit bigger. At the top here, you can see that you can download them, so I would recommend that you do that and go through this notebook if you're interested in solar-like oscillators. And I think Cole will talk you through some of the things that we see in here.
Right. Well, so I think the first thing is if we scroll just back up a little bit to the very top, you'll see under these learning goals, you see something that says nu max. So that's the Greek letter nu. Looks like a V, and then this delta nu. And then these two things are very important because if we can measure these, then we can get an estimate of the star's mass and radius, just as the title of this notebook says, right? So I'm gonna try to explain what these things are, and hopefully Nora will also draw an accompanying plot to show these, just so it might be helpful that way. But now, so you can read through this in your own time. But the first thing that we're going to do is in this case, we're just going to find a light curve of a star. So we can see here, this is a star that was originally observed by Kepler, and we need the short cadence observations, the one where we have a data point every 1 minute. And then we're going to download them all, stitch them together, and then, as I said, if you just look at the light curve, it's actually really difficult to see if there's anything happening. So we're just going to go right to the periodogram, and light curve has this lovely function that is called toPeriodogram, and you're going to put in these parameters, like, so you have normalization, PSD, that actually is just a set of units that are convenient for people who work with sun-like stars to work with. And then we'll see this plot here, and as you can see, there's so if you recall from our episode or Nora and Cassie's episode, on the periodograms, each one of these peaks represents a frequency at which the star is varying. So you have a lot of noise, and then you just have these very distinct peaks popping up. And the immediate thing that you can see is that it kind of has this general pattern to it, where it gets stronger and then gets weaker. The amplitude of those peaks gets higher. And the other thing is that we see that they're very regularly spaced. And this regular spacing is known as delta nu. It's called the large separation. Again, because us asteroseismologists are really original in our naming. So this large separation, it gives us a way of looking into the interior of the star and saying what the sound speed is within the star. So this is roughly how long it takes a wave to cross a sound wave. So just like my voice in this room, how long it takes a sound wave to move across the star. And that is encoded in these separations in the regular pattern that we see here, this very comb-like pattern, right? Now, the other thing that's in here is this property that's called nu max, or the frequency of maximum oscillation power. So you'll see, as we said before, this is kind of like this triangle-ish shape, as you can see, as Nora's pointing out for us. And we want to find something that's quite kind of like the center of this, and that is the frequency, yes, of maximum oscillation power. Now this is just directly related to the size of the star. So between these two properties, we have a way of relating these to the mass and the radius of the star, or to the size and the density of the star more precisely.
Which is what we want when we're looking at exoplanets.
Exactly, and that's why these kinds of stars and analyzing these kinds of stars is so complementary to exoplanet studies. So, it used to be a very individual thing where people would have to write their own code and figure out how to do this, but Lightcurve has put this all into an amazing little package that you can they have the commands for you right there, and they give you this beautiful demonstration where they show you this thing called, they have the orange arrows pointing down that show you the frequencies that are all in this pattern.
So the distance between two of these red lines, that would be nu max. Sorry,
delta nu.
Delta nu. That would be delta nu.
Yes, that is delta nu. That is the frequency. That is the large separation.
Mm-hmm.
And then the center of this hump-like feature, the mode envelope, that is nu max.
So the top of this blue curve.
Yes, that is the where the top of that curve occurs. That's the frequency of maximum oscillation power. Right. So this helps us determine what those two values are, and then we can just scroll on down.
So the lines of code up here, you don't necessarily need to run them. The important lines of code are these ones here. So this is just plotting it. And then in the next line of code, this is just the coolest part of Lightcurve. It lets you determine these values of nu max and delta nu automatically. You don't have to calculate nu max or delta nu. You don't have to look at the graph and measure the distance between two different peaks. All of that is just done completely automatically within Lightcurve. So that's really, really useful. So you can see here, you can get the value of nu max with literally this one line of code. So you just do seismology.numax.value, and that's it. And then it will tell you what that value is. And we'll get back to how we use that value in just a moment. You can also, if you want to diagnose, they call this diagnose nu max, you can get this 3-paneled figure here that we see. We won't go into it in too much detail. I think the most important one of these panels, maybe Cole will have a different opinion, is this bottom one. So you do want to see this nice, it's called a Gaussian trend, this nice like hump or curve, because if you don't see that, then the value of nu max that you're getting out probably isn't correct. So if you're seeing a flat line in that last panel there, it most likely means that the data isn't good enough to be able to determine nu max, or there just isn't an asteroseismic signal in that data. So maybe do have a look at that plot, that final panel of that plot, and make sure that you do see a nice peak, because that's what we're looking for.
Yeah.
Cool. So very similar. We also want to get the frequency spacing, so the spacing between those two spikes, which we can, again, we love Lightcurve, we can get with just one line of code. So instead of determine nu max, we are determining estimate delta nu. Which, as we said before, is that spacing between two peaks. So again, you can run these diagnostic plots, and again, you just want to make sure that you do actually see the signal in these what are they called? In these periodograms, and that if you can't see that signal in that periodogram, the code probably can't see it either. So do just make sure that the values you're getting out do seem sensible and do seem like they could be determined from that data. Because very importantly, not every star will have solar-like oscillations. Most stars will not have solar-like oscillations, but some stars do, and if they do, it's really, really cool. So keep that in mind.
Yes, absolutely, Nora. So thank you for bringing us through this. And I think, one of the really cool things about just having these couple of lines of codes, these two functions that give us the nu max and the delta nu values, is that with these in hand, we can just do a very simple calculation, and then these two values actually give us the mass and the radius of the star. And then this is how we relate it to your planet studies, right? So maybe if you scroll down a little bit, yes, there are these equations here that people have derived in some papers in 1995. And all that you really need to know from this is that we have these observed values of nu max and delta nu as you see them in those equations. And then we can relate these directly to the mass and the radius of the star. Little caveat, we also need a temperature, you might have noticed, but we can take that just directly from the test input catalog.
So from ExoFOP.
From ExoFOP, or from if you have a latte report for this already, you might see, you might have this in one of the tables in your report.
Yep, and then so once you have that value of the effective temperature, you can just estimate the mass. We'll run these 3 lines of code, and there you have it. You can estimate the mass, the radius, and the log g, which is the surface gravity. So how heavy you would be on one of these planets.
Yeah, so I mean, this is exactly what we want. And then in this example, you see that they have values for, as you scroll down just a bit, line 15 there, you see that you have something for nu max, something for delta nu, and then these estimated values for the mass, the radius, and the surface gravity of the star. And typically, this would take months of follow-up observations to try to get a spectroscopic value for some of these, and there's problems with that. So one of the really cool things is that you just have it right there.
Yeah, so these values might differ slightly from the values you see on ExoFOP, for example. Cole will tell you, as he always tells me, that these values that we get from asteroseismology are much better and much more precise, so we should believe these values are not the ones on ExoFOP. That being said, we can use the ones on ExoFOP too.
Yes, so you can use the ones on ExoFOP in the case where you don't have another alternative. But the seismology is very precise, it's very finely tuned by the properties of the star. And then so if you have the asteroseismic values, you should always trust those over the color values that are given through ExoFOP. Absolutely. At least that's my take on the matter.
He might be biased, he studies this.
No,
he is correct. All right, so I think that was really useful. I would recommend going to Lightcurve. Again, we'll put the link in the chat, and just having a look through that notebook. There's a lot of other information just on that website that will about things that we haven't covered today. But it is really cool. Again, I will just mention the caveat that most stars will not show solar-like oscillations, so don't expect to see them in all the stars you look at from tests. But if you do find them, they are really, really cool and definitely can be used to derive these really important stellar properties that relate back to
exactly. So what we should do is, if you want to look for these, you download the light curve of your favorite solar-like star, you pass it to a periodigram, and then you just look for these lines, these frequencies, these peaks at high frequencies for you to be able to try to identify these solar-like oscillations.
Yeah, and the code in that notebook that we just saw will let you do that with TESS or Kepler data. So instead of putting in KIC and that number that we just saw, just change that to TIC, or your favorite TIC ID that you think might have solar-like oscillators, and give it a go. All right, I think that's it for today. So thank you, Cole, for joining us for another episode, and see you again soon.
Thank you for having me. I had a lot of fun.
Bye.